Good evening, everybody, and welcome to our Curious Mind show tonight. Good to see a good turnout, and I'm really glad that we're back in business with some really great speakers this year. So, a little bit of housekeeping to start with. There will be a question and answer session after Dr. Richmond has given his talk. If you could please, if you got any questions, the preferred way to do it is type them into the chat. If you do that, then Michael, who's our host at CPK, will forward the questions to Alistair. If you can't do that, then if you use the Wave facility, I don't know where that is, okay? But apparently there's a way for, if you do that, Michael will see you, and then you can ask a verbal question. But to keep things simple, we'd prefer the questions on chat. So this evening's speaker is Alistair Richmond from Edinburgh University. And Alistair is, he's a graduate of Aberdeen University. Actually, when I checked out his bio, it said that he's a threefold graduate of Aberdeen University, which I suppose gives you something in common with Prince Charles.
Oh.
Yeah, I believe he's a big fan of the 3 degrees as well. Anyway, that was my terrible joke for the evening. Okay. Anyway, so Alistair he works in the philosophy department at Edinburgh University. His interests are, well, I guess actually, and correct me if I'm wrong, but appear to be in the field of metaphysics. Now, I have to say, as a physics graduate, I'd always thought of metaphysics as something that medieval kind of sorcerers would engage in, yeah? But anyway, I checked out what it means, and it's actually, I reckon I could probably talk to Alistair for weeks and weeks on end about stuff. Metaphysics is the philosophy of being, of space, time, the nature of consciousness, and the relationship between mind and matter. And I know that there's quite a few people in our society who are just dead keen on asking complicated, difficult questions about that. Anyway, I've looked at Alistair's publication list, fabulous stuff, not only time travel, the doomsday argument, that must be a whole lot of fun, okay? And he's written articles on Doctor Who. Anyway, tonight he's going to tell us about his philosopher's guide to traveling in time. So I'll hand you over to Alistair, and then at the end of the talk, we'll do the Q&A session. Alistair, over to you.
Thank you very much, John. It's a great pleasure to be talking to you this evening. Give me one moment while I summon my slides, and then I hope you will have something to look at other than my face for the duration of the. There we go. So just to check that's right. Yes, as Tom said, I'm a philosophy lecturer. I am by no stretch of the imagination a scientist or a physicist, although I'm very interested in science, very interested in physics. My particular beat is the philosophy of time travel, which is a branch of philosophy, but actually is a subject devoted to looking at interesting philosophical problems. And I thought it would be fun just to start us off by giving you a quick guide to how philosophers approach the subject. Searching for a suitable visual image to start us off, I found this from the X-Men. This is one of the X-Men who's actually a member of staff at Edinburgh University. If time travel is possible, if as a result history is mutable, we'll have to redefine our concept of reality itself. Heady stuff. Moira McTaggart, fictitious Nobel Prize winner, Edinburgh University, Uncanny X-Men, 1980. I'm not going to offer you any advice about how to change history, how to alter past events. I'm going to explain to you how time travel doesn't necessarily mean that you can do that. So I'm sorry if that's kind of disappointing for anybody. I'm sure all of us can look back at history and have a few changes in mind, personal or political or global, but sadly that may not be something that philosophy or physics allow. So without further ado, a quick outline. First of all, how to define time travel. What is time travel? How is it different from simply getting older? I'm going to talk a bit about grandfather paradoxes, the classic argument against traveling into the past, the one that says if you could travel into the past, you could go back in time and eliminate your grandfather or some other ancestor and thereby prevent your own existence. I'm going to talk about causal loops, which are cases where, again, involving backward time travel, an event turns out to be in part a cause of itself. Then I'm going to talk a little bit about the physics, how physicists approach these issues, because it's really the interest that some physicists have taken in problems involving time travel that I think has really made the subject interesting. Not, taking it out of the realm of science fiction, fascinating though science fiction can be, and made it into a subject that's sort of academically interesting. I'm going to talk about things called closed time-like curves, which are basically physicists speak for traveling into the past. I'm going to talk about the possibility of traveling backward in time across a range of many worlds or different histories. I'm going to talk about an argument in favor of many histories time travel that appeals to a thing called the autonomy principle. I'm going to talk about a couple more exotic possibilities, like there are many different dimensions that time has. That's one that some philosophers and physicists have considered. And then I'm going to close by outlining a couple of fictional examples. And after that, if any of you have chosen to hang around, I'd be delighted to take any questions. I'm going to aim to talk for around about 50 minutes, or at any rate, no more than 50 minutes. So if I'm still going in 53 minutes, alert me and I will stop. So that's the outline. Time travel, grandfather paradoxes, causal loops, closed time-like curves, many worlds travel, the autonomy principle, many times, and inconsistent realities. And that should fill up 50 minutes, I hope. So, best definition of time travel I know is due to a now sadly deceased American philosopher by the name of David Lewis. And Lewis said that in order to travel in time, you need a distinction between two ways of registering time, what he calls personal time and external time. Personal time is time for you, time for the traveler, and it reflects everything that's traveling with you. So personal time measures how your watch is progressing. It measures how your memories accumulate, how your digestion accumulates digestive products, how your hair greys or your cells decay or your clothes wear and tear. External time is time in some suitable other frame of reference, some non-traveling reference frame. It could be Greenwich Mean Time, it could be the time on Big Ben, it could be British summertime, it could be a more inclusive sort of geological time. You could look at the movement of the stars and galaxies if you wanted a really inclusive measure of external time. But basically, personal time is time for the traveller, and external time is time in the world at large. Now, those of us who are not time travellers are not aware of any difference between personal time and external time. If you're not a time traveller, your personal time and your external time march along in lockstep. 5 minutes of personal time passing measured by your watch, the accumulation of your memories, your cellular decay, the wear and tear in your clothes, should match 5 minutes measured in the outside world. 5 minutes registered by Big Ben, 5 minutes registered by the rotation of the Earth, 5 minutes registered by the motion of the Earth around the Sun, etc. So what it is not to be a time traveller is to have personal time and external time marching along hand in hand. Time travellers, if there are any, are people for whom personal time and external time come apart. As Lewis says, any traveller departs and then arrives at his destination. The time elapsed from departure to arrival, positive or perhaps zero, is the duration of the journey. But if he is a time traveller, the separation in time between departure and arrival does not equal the duration of the journey. Suppose I activate a machine and I time how long the machine is in operation. And I time it for exactly 5 minutes. 5 minutes increasing personal time, using all the measures I mentioned a minute ago. And I step out of my machine and find that it's now 2071. And that what was a 5-minute interval for me has turned out to be a 50-year interval in the external world. Well, by Lewis's definition, I've travelled into the future. I am a forward time traveller. Backward time travel, the one that seems to pose all the really interesting problems, is where your personal time is positive. It increases during the journey. But you find when you get out of your machine or you step out of your wormhole or whatever, that you haven't arrived at a later time, you've arrived at an earlier time. In backward time travel, viewed in external time, you arrive before you set out. So if I were a backward time traveller, I activate my machine, I record 5 minutes journey time, and I get out to find that I'm actually in 1971. And I've moved backward 50 years in external time. Well, in that case, I'm a backward time traveler. So forward time travel, personal time and external time are both positive, but they have different sizes. Typically, people are interested in cases where you have a small interval of personal time and a much bigger interval of external time. So you spend 5 minutes traveling 50 years into the future. Nobody seems to be very interested in spending 50 personal years traveling 5 minutes into the future. I think you would feel a bit silly if you invented a time machine that allowed you to spend 50 years getting older, reaching a time 5 minutes after you set out. But that would be time travel too. So personal time and external time share the same direction, but they have different durations. Backward time travel, the journey in external time ends before it begins. Viewed in external time, the journey has a negative duration. And that's very strange. Backward time travel seems to pose all the problems. So, just get the slides to work. Hold on. There we go. The first thing, and probably the last thing that a lot of people think about when they're presented with backward time travel is the grandfather paradox. And the grandfather paradox has been the subject of innumerable films and stories. But the basic idea is, if you could travel backwards in time, you could eliminate your grandfather, or one of your grandfathers, before grandfather had had a chance to become a father. So you eliminate one of your grandfathers, that grandfather doesn't have any children, so at least one of your parents is missing, so you're missing. So if your mission succeeds, you're not there to carry out your mission. Behold, a paradox, something inconsistent. So logic seems to forbid grandfathers who are both alive and dead at the same time. The classic answer to this is from this gentleman, David Lewis, whose discrepancy definition of time travel I gave you a couple of minutes ago. And David Lewis says, well, the grandfather paradox argument makes a mistake. It says, if you could travel in time, then it would be possible to do things like eliminate your grandfather before your grandfather had had any children. But why think that that's what time travel would let you do? Why assume that just being in the past would let you make paradoxes happen? In other words, Lewis says, it's only possible to kill your grandfather relative to some facts about the situation. Suppose you travel back in time and you point a gun at your young grandfather to be. Well, some facts about the situation might make it look like you can succeed. You know, grandfather isn't bulletproof. He's not wearing a Kevlar vest. Let's assume that you've got a keen eye and a functioning gun. So relative to those kind of facts, you're successfully eliminating grandfather to be seems possible. But suppose you plug in one more fact, the fact that this man is going to go on and be your grandfather. Relative to that fact, suddenly your succeeding is not possible. So it's not that time travel would necessarily let you create paradoxes. It's that the appearance of creating paradoxes arises from forgetting that something can be possible relative to some set of facts, but not others. But that of itself is not very strange. You know, it's a commonplace that one and the same event, one and the same outcome can be probable relative to some set of facts, very improbable relative to another. I mean, to take an example, I'm keen to stay in good health. And so my chances of maintaining good health are going to be relative to various facts about me. Now, relative to the fact that I don't smoke and hardly drink and exercise regularly, the chances of my enjoying many more years of good health are very high. But relative to the fact that my diet's pretty bad, my chances of enjoying good health somewhat lower. But there's no paradox here. You know, it's like, can I stop smoking? Here's a way to think about it. Can I stop smoking? Well, there are self-help groups, there are self-hypnosis tapes, there are Nicorette patches and similar to help people over the pangs of nicotine withdrawal. So relative to facts like that, it should be possible for me to stop smoking. But there's a very important logical problem standing in the way of my stopping smoking, namely that, as it happens, I don't smoke. So relative to some facts, my stopping smoking is possible. Relative to a more inclusive set, one that includes the fact I don't smoke, then it isn't possible. But there's no paradox here. So Lewis says, backward time travel doesn't necessarily mean that you could eliminate your grandfather to be. It just means that anything you do in the past is consistent with the past whence you come. So if you travel back and you try to shoot grandfather, you're guaranteed to fail, because the past already contains your failure. The past you come from already contains your attempt at assassinating grandfather and that attempt failing. Now that might look very strange, particularly if you try repeatedly to assassinate grandfather, or you try repeatedly to assassinate your earlier self. It may look as if there's a whole string of coincidences pile up to prevent you making history different. But that oddity doesn't mean that it's impossible. It just means that the conditions will be very constrained. So Lewis's way out of grandfather paradoxes is to say, no, time travel doesn't mean that you could make history different from what it was. Time travel is possible provided you become part of the history that did exist. You can't change history, you can't overwrite history, but you can fulfill history. You can be part of it. So again, time travel is possible provided travelers' actions are consistent with their native history. Now that may look very strange, but very strange is one thing, and impossible is another thing. So one of the really worrying other cases is the case of the causal loop. And again, there's quite a few of these in fiction. The example showed on the board in front of you, the diagram comes from Michio Kaku's book Hyperspace. And that is the career through time of a time traveler from Robert Heinlein's, spoiler alert, Robert Heinlein's short story, All You Zombies, who contrives to be both her own parents. The precise mechanism I leave to your imagination. But a causal loop, again, is a feature of backward time travel and is an event that manages to be its own cause or among its own causes. Lewis has a nice example, which I'll embroider a wee bit. Imagine that you're sitting at home one evening and the phone rings and you answer the phone and a strangely familiar voice says, don't say a word, write these instructions down and follow them to the letter. And the voice then gives you some instructions, which turn out to be instructions for building and operating a time machine. And you follow the instructions and they work. And you find that you've arrived in the recent past. So you think, I know what I'll do. You call your own phone number when you're in the past. An oddly familiar voice says, hello. And you say into the phone, don't say a word, write these instructions down and follow them to the letter. And you proceed to give your earlier self the instructions for how to build and operate a time machine. I'm sure you could see where that story was going, but you get the idea. Now that isn't inconsistent. There's no overwriting of history. There's no grandfather who's alive and dead at the same time. But there's still something powerfully strange about this. And that is, where does the information come from? Who actually makes the time machine? Where do the instructions come from? And Lewis's answer to that may not strike you as terribly satisfactory on a first hearing, but it's quite an interesting answer. Lewis says, well, look, where does information come from in any sequence of cause and effect, right? There only seem to be a certain limited number of ways that causes can follow effects, right? One way is you have an infinite chain, that every cause has a cause, 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 ad infinitum. Each event has a cause. But you start asking, where does the whole chain of events come from? And it's not clear that there's a good answer to that. It's not clear that there's anything further that you can appeal to. So that's one kind of chain, an infinite straight line. Another kind of chain, and this is one taken seriously by physicists, is where you have a finite straight line, where you have a cause of a cause of a cause, and then you hit a wall with an event that is a cause but doesn't itself have causes. And some readings of quantum mechanics say that there are events like this that occur all the time, events that are purely spontaneous. There's no initiating cause, there's no determining cause. If you're interested in classic Big Bang cosmology, you may have heard Stephen Hawking's lovely analogy that asking what came before the Big Bang is like asking what's to the north of the North Pole. In other words, the Big Bang isn't an event in time, it's a limit to how far events can be traced back. It's the origin, if you like. So just as there's no north of the North Pole, there's no earlier than the Big Bang in classic Big Bang cosmology. So the question, what caused the Big Bang, doesn't have a well-defined answer. There's nothing earlier to appeal to. And so Lewis says, well, an event being among its own causes is powerfully strange. And it would be a serious offence to our ideas about how information gets transmitted and shared. But don't try to worry yourself about where does the information come from in a causal loop, because causal loops are no more, no less easy to explain than any other kind of causal chain. If a causal chain is infinite, causes of causes of causes of causes ad infinitum, each event may be explicable, but the whole chain of events isn't explicable. Similarly, if you have a finite chain in a straight line, causes of causes of causes, then you hit a wall like the Big Bang, an explanation seems to give out. So says Lewis, causal loops are powerfully strange, but they're no less explicable than infinite or finite straight line causal chains. I'm going to talk a little bit about the physics, just to give you a sense of why physicists are interested in this stuff. This here, as many of you may no doubt know, is a representation of how relativity treats movement in space and time. The light cone diagram. Every point in space and time has a characteristic structure around it, determined by a pair of cones. Imagine that time is the straight line running vertically up the slide, the one labeled time. And imagine that space is the two horizontal axes shown. If you were to sit still at the point labeled observer and just get older, you would simply move up the time axis in a straight line. Not a very exciting journey through the universe, but easy to describe. If you were to move, suppose you were to move to the right-hand side of the diagram at a uniform speed and on a uniform heading, then you would have a straight line journey from the point labeled observer. The boundaries of the cones are set by paths that either leave the observer point or converge at the observer point at light speed. Right, so the boundary of the topmost cone is all the points that leave the point labeled observer moving at the speed of light. And so that cone, assuming you can't travel faster than light, sets the boundaries to the regions of space and time that you can send signals to. Hence it's called the future light cone. It's the region of space-time you can affect. The converse are all the regions in space-time that can send signals to you, and that's the past light cone. So the boundaries of the past light cone are set by all the light rays that can converge on the point labeled observer. So the idea is that the light cone structure determines where you can send information, where matter and energy can be transmitted. So every point has a light cone structure, and you can send a signal to anything within the future light cone, and you can receive a signal from anything within the past light cone. But you'll notice that those two cones don't overlap. You can't send a signal into the future light cone and have it arrive in the past, at least not without exceeding the speed of light. So one of the things that the speed of light does is it's a wall against traveling into the past. Or is it? Well, this is the sticky bit. The special theory of relativity says that light cones are parallel all across space and time. Different observers travel at different velocities. None of them travel faster than light. But the different light cones are all parallel, one with the other. So you can't send a signal into your future and have it travel via someone else's light cone into your past. The general theory says, however, that the structure of space and time, literally the future and the past at any given point, are affected by the presence of matter. That's actually the effect that we describe as gravitation. Gravitation is the changing of light cone structure, the curvature of space-time. So the idea is that if you have a great deal of mass and it's moving very quickly, then it's possible that light cone structure can distort. A very dense object, a future light cone will tilt towards it. If your mass is very, very big and or very, very dense, then future light cones will tilt so far that they will diverge substantially enough from their surroundings that you get a thing called a closed time-like curve forming. A closed time-like curve is a journey through space and time that never exceeds the speed of light, but returns to the very point whence it departed, like that. Imagine that those are future cones in a seriously curved space-time. You can travel from cone to cone to cone to cone to cone without exceeding the speed of light, without, locally speaking, traveling backwards in time, without violating the restrictions of special relativity against superluminal travel, and yet you arrive at the very point whence you departed. So a closed time-like curve is, physicists speak, for backward time travel. It's a journey through space and time that doesn't involve exceeding the speed of light, that nonetheless takes you back to the very point in time whence you began. So you can interact with your earlier self, or if you go on a slightly longer curve, you can interact with your grandfather, your great-grandfather, or indeed dinosaurs, if you're so minded. In 1949, the Austrian logician and mathematician Kurt Gödel solved Einstein's general theory of relativity for a whole family of universes which are stuffed full of closed time-like curves, riddled with closed time-like curves throughout. You can travel between any 2 points in space and time as often as you like. Gödel's universe, however, almost certainly isn't ours. It's a model universe, and it's a very unrealistic model universe. For one thing, Gödel's universe is infinite. It looks like ours is finite. Gödel's universe is non-expanding, and ours looks like it's expanding. And Gödel's universe is rotating, and our universe seemingly is not. So Gödel's universe, for all that it's one massive time machine, those time-like curves through every point, sadly is almost certainly not a universe like ours. Wind forward to 1973, though, and the American physicist Frank Tipler solved Einstein's general theory of relativity for a local closed time-like curve generator, where you take an incredibly dense cylinder and you spin it very, very rapidly. It's so dense that if it wasn't spinning, it would collapse in on itself and form a black hole. But you spin it very, very fast, and the gravitational effect of the cylinder tilts local light cones, so you get a shape like the one on the slide in front of you, where local future cones tilt so far that you can travel back to the very point whence you started. So physicists accept that Tipler's time machine is a relativistically possible model for generating closed time-like curves. The problem is that it's got some assumptions built into it. One is that it's very, very dense. It's something like 10 to the power 40 to 10 to the power 80 times denser than the matter in an atomic nucleus, which is tough. It's got to be spinning so fast that its surface is moving at least 50% of the speed of light, which is very tough. But the killer condition is that in Tipler's original model, the cylinder is infinitely long, which is very, very tough indeed. So I think it's fair to say that Tipler's cylinder is not a very realistic prospect for being able to travel in time. Now, scientists have uncovered an awful lot of other closed time-like curve generators within relativity and also quantum theory, but they're all of them in some degree unrealistic. There's something funny about them, like they involve an infinite amount of matter, or they involve matter doing things that ordinary matter can't do, like they require matter that's gravitationally repulsive rather than attractive. So closed time-like curves are an interesting subject for physicists to study, but no one's got a practical one. And generally, physicists think that the way to deal with the apparent paradoxes of closed time-like curves is something like the David Lewis method that I sketched earlier, to say you can travel into the past and interact with yourself, provided that the history you arrive in is consistent with the one whence you come. So I think it's fair to say that a lot of physicists who study these things have opted for something like the David Lewis answer. You can travel in time, forward or backward, provided that the history you arrive in is consistent with the history whence you come. That you can fulfill history, you can affect history, but you can't change it. You can't erase your infant grandfather to be, you can't erase your earlier self, but you can interact with them. Now, some physicists don't like this idea at all. Here's a physicist who doesn't like the Lewis model. This is a physicist, I think he's based in Oxford now, called David Deutsch. And Deutsch has adopted, for physical reasons, a model whereby backward time travel only makes sense if you arrive in a different universe from the one that you left. A many worlds interpretation of time travel. Deutsch also supports a many worlds interpretation of quantum theory. So basically, Deutsch says you can only travel in time if the point you arrive in is in a different world, a different history. And Deutsch thinks this is okay because, and I quote, other times are just special cases of other universes. All other times are effectively distributed across a system of many worlds. So the idea is that you get into your time machine and you travel into the past, but the past you arrive in is a distinct past from the past that you come from. In other words, you can interact with a counterpart of your past. And when there, you can shoot your infant grandfather to be, or at any rate, stop him meeting who would otherwise be your grandmother. You can assassinate your earlier self, secured in the knowledge there's no paradox, because the dead grandfather and your grandfather inhabit different realities. And this seems to offer an answer to the information loop problem as well. Because in this world, if you travel back in time, you're displaced into an adjacent universe. So if you phone up your earlier self, you're not literally talking to your earlier self, you're talking to your earlier self's counterpart. So you're not really generating information out of nothing. So David Deutsch thinks that basically the constraints on a Lewis time traveler, a single world time traveler, would be so strange that they would involve violating what we think of as well-founded physical principles. He thinks that there are certain things built into physics that we take for granted when we're designing experiments, when we're observing the world, that just wouldn't survive if history is constrained in the way that the single world model suggests it should be. This is the autonomy principle, is it? Basically, Deutsch says that what an object can do should be a function of local facts about that object. I mean, I have in my hand a pen, if you can still see the camera feed, but I presume that the causal powers this pen possesses to write or not to write are a function of local facts about the pen, like how much ink it's got in it. But if you start taking ordinary objects back in time, then suddenly they lose their autonomy. You take an ordinary gun, a gun that seems to be able to work fine in the present day, you take it back in time and point it at your infant grandfather, and it's guaranteed to fail. And that guaranteed failure, says Deutsch, violates a principle that we think governs physical objects, that they're autonomous, that only local facts about how objects behave shape what we can do. This is a quote from a paper that Deutsch co-wrote with the philosopher Michael Lockwood. When we strike a match, we do not have to worry that we might be thwarted because the configuration of the planets, say, might be inconsistent with the match being lit. If you travel in a single history, systems that should normally function perfectly fine suddenly stop being able to function normally. And that, which in Lockwood, would be an intolerable restriction on the physical powers of objects. So basically, any realistic physics, they say, that governs backward time travel must involve displacement into an alternative world, another history. If travel does involve displacement between worlds in a system of histories or multiverse, to take a currently fashionable term, there are no restrictions on time travelers. Go back and point as many guns as you like at your grandfather's counterpart, because anyone you kill is not literally part of your past. So this is a quick illustration. You imagine that time is linear up to the point at which the traveller arrives in the past. The traveller leaves world A, lands in world B, assassinates world B's counterpart of himself, and thereafter goes on the sole survivor. Now that may look very strange from the perspective of somebody in world B, but if you could see both realities, you would see that the traveller from world A is a perfectly normal traveller. He has an ancestry like anybody else. So this is supposed to remove the kind of problems that we saw associated with the David Lewis model. Right? So the idea is if you've got many histories, there's no problems about consistency constraints. There's no problems about trying to assassinate counterparts of your grandfather or your infant self. And there's no problem about where any information comes from. The information may come from another world, but otherwise it's perfectly normal. There's no causal loop funny business, if you like. This is a slightly more exotic possibility, more discussed by philosophers, I think, than physicists, but it has been discussed by physicists too. This is the idea that time, that mysterious thing, may not be the straightforward single line that we like to think. This is a theory of multi-dimensional time, according to which time is more like a plane. You know, it has extension in two orthogonal right angle separated directions. So on this view, each moment has a different past associated with it, right? So on this view, growing older involves moving across the temporal plane at a rate of 1 normal second per 1 hypersecond, right? You have seconds running horizontally and hyperseconds running vertically up the diagram. So on this view, normal persistence is just getting older at the rate of 1 normal second per 1 hypersecond. Time traveller is somebody who can travel across the temporal plane at a different angle or a different speed. So suppose you set out from the point labelled T2 on line P2, and you jump back in time so that you arrive at P3, where P3 intersects with T1. So you jump from P2 T2 to P3 T1. Well, there you arrive in our past, but it's a past distinct from the one whence you come. So the idea is that if time is multidimensional, you would have some of the same benefits as you would have in a Deutsch-style many-world system. The time you arrive in is in a different part of the plane from the time that you left, so it's literally a different past. Each moment has a different past associated with it. So you can arrive at a different time, a different timeline from the one whence you come, and therefore there would be no restrictions. I tried to illustrate this with reference to a time travel science fiction novel, which I'm particularly fond, by a science fiction writer called John Brunner. This is a novel variously published under the name of The Society of Time or Times Without Number. And it imagines that time has two independent dimensions. And Times Without Number is the story of a man who's sent back from a world in which the Armada won to try to thwart somebody who's aiming to undercut the Armada's victory. And in order to do that, he travels across a second dimension of so-called speculative time. But he finds, to his cost and to his horror, that he's been anticipated. And as he's waiting for history to adjust itself around him, he finds himself thinking, wait a minute, why has my history received no visitors from the future? And he reasons thus: human nature being what it is, original sin being what it is, if you like, there would sooner or later come a time when the temptation to amend the past would lure someone into tampering with the course of events which led to the actual discovery of time apparatus. In other words, if you could alter history, eventually somebody would keep pushing the alteration of history to the point where they undermined the ability to alter history itself. In other words, being able to change history, whether through many time dimensions or some other device, would become unstable. You wouldn't expect a history like that to survive. One quite exotic possibility might just be to accept that travelers can make the world inconsistent. This isn't a many histories view or a many time dimensions view, but it's one that looks to some interpretations of a quantum theory, sometimes known as retroactive versions of quantum theory, according to which observation doesn't just fix the present properties that a system has, it can actually reach backwards and determine the properties of events in the past. And in the so-called modal interpretation of quantum mechanics, one that takes possibilities seriously, that thinks that possibilities are real things, if you open the box containing Schrodinger's cat now and observe that the cat is dead, that doesn't prevent you carrying out a subsequent observation later in which the cat proves to have been alive all the time. So armed with this kind of understanding of the quantum possibility, according to which present observations or even future observations can collapse past events, then not only would dead cats not stay dead, but the consistency of reality would be subject to future retroactive change, including presumably all this. As the slightly worrying implication that not only would the events of the past be amenable to future overwriting, so might the events of the present. We seem to have no reason to think that we are any more stable or any more fixed in history than anything else. I stress that this exotic interpretation of quantum mechanics is not necessarily a very popular or very strongly supported one, but it is something that physicists have taken very seriously to make sense of how quantum systems behave when they're measured. And it might afford a way of making sense of being able to go back in time and actually alter history to make the very paradoxes occur that Lewis said were impossible. Well, I promised I wouldn't talk for longer than 50 minutes. I think I've actually talked for around about 42. So without trespassing too much further on your time, I will simply say thank you. I've brought bring my presentation to an end at that point. And over to you. Thank you very much.
Right, Jings. How complicated, yeah? Yeah. So if anyone's got questions, please feel free to type them into the chat, okay? Or raise your hand and we can we can deal with your questions. I'll start. I found that quite complicated, I mean, I've been thinking about this time thing quite a lot, and obviously a lot of other clever people have been thinking about it much more than I have. Okay, can I just ask you a question? It's kind of about time travel, yeah, but it's not directly about what you've spoken about right now. But what is this weird phenomenon called the present? Is that a stupid question, or can I ask that?
No, it's. I'm tempted to say that not only is it not a stupid question, it's pretty much the only question in the philosophy of time. Because I mean, I showed you the light cone diagram, didn't I? That well-defined future, well-defined past, and there's this tiny little point where the two meet. Well, that tiny little point is the one where all our experience happens. the tiny little point is the point where we take in experiences, sensory events register on us, in which we actually act and intervene in the world. So while people have been tempted to argue that the future doesn't exist, or the past doesn't exist, or both of them don't exist, I mean, a lot of people are what philosophers call believers in presentism, which just says that the only things that exist now. The things in the past used to exist, things in the future will exist, but they don't literally exist. Literal existence is confined to what's going on right now. Presentists exist. There are lots of them. There are people who think that the past exists and the present exists. So as time passes, reality is kind of getting bigger. Each moment is like a new sliver of reality. But nobody has wanted to argue that the present doesn't exist. The present seems to be fundamental, because that's where we make our decisions. That's where our experiences happen. And yet, a lot of physics doesn't seem to leave room for a well-defined present. I mean, Einstein famously thought that other times are like other places. The people who live in other times are like people who live in, other cities. I mean, I'm in Edinburgh. Where I am, Edinburgh is here. For those of you who have the good fortune to be in Perth, Perth is here. People in Arbroath, for them, Arbroath is here. And if Einstein is right, the word here is like the word now, or the word now is like the word here. Other people live in different nouns. So what the present is, I mean, it's easy to point to. Here it is going on around me. Here it is going on around me. It's the immediately given, the lively bit. The bit I can actually experience and interact with. But what it is, whether it's the sum of all reality, if you're like a presentist, whether if you're a growing block theorist, it's the edge of reality, the bit where things become real, it's very difficult to say. But you'll notice that I didn't begin by offering you a definition of time. I just said, here's two ways of registering time, personal time and external time. And there's a reason for that, because I find it easier to define time travel than I do to define time. So your question about what is the present is not a silly question at all. It's just hang of a difficult to answer.
Amazing. Okay, so I believe Michael Allnut has a question.
Oh yes, thank you. How careful are writers of the likes of Doctor Who to fit into theories such as you have outlined? Some of them are very careful. Others just don't care. The thing is, I mean, I'm extremely fond of Doctor Who. Sitting on my desk is a USB hub in the shape of a TARDIS. Right? I yield to nobody in my now 50-year fascination with Doctor Who. But some weeks you can change history, and some weeks you can't. And the thing with Doctor Who is that some weeks it's inconsistent, some weeks it's not inconsistent, some weeks you can't tell. It's not even consistently inconsistent. There are some time travel stories, though, that really do take consistency very seriously. If any of you have seen the Terry Gilliam film 12 Monkeys from 1995, that's, I think, completely watertight. There's no grandfather paradoxes. There's no overwriting of history. There's no inconsistencies at all. I mean, it runs like clockwork. It's very unusual to do that. Normally, I think Doctor Who just doesn't care whether it's consistent. I mean, you get some chat about, oh, we can't change that because it's a fixed point in history. If those of you who remember David Tennant going to Pompeii, which is one I enjoyed. And he muses over rescuing people from the eruption of Vesuvius. And he says, oh, no, I can't do that. It's a fixed point in history. Well, all a fixed point in history is one that the audience heard about in O-grade history, I think, as far as I can tell. It's not actually a thing. A fixed point in history is just something Doctor Who writers made up. So some of them actually are very careful to make them internally consistent. Many of them are not. My favorite examples of consistent time travel tend not to be from Doctor Who. They tend to be films like 12 Monkeys. May I move on to the next question?
Yeah, David Waller.
Well, thank you, David. How long is the present? Well, some of that you need a psychologist to answer. What's the minimal difference between successive mental events? Some of it might be for the metaphysician. I mean, if you are, for example, I'm a presentist, then you can imagine that there is a certain minimal extent that separates the two voids of the past and the future. The problem is that different measurements that we keep coming up with seem to come up with slightly different suggested durations. I mean, some of them put it down very, very short intervals of time. I mean, quantum physics, the minimal physical unit of time, the Planck time, is infinitesimal compared to human perception, which strongly suggests that what we think of as the present is actually a very, very long and extended thing. And we're quite familiar with the idea that the subjective present varies according to circumstances. If you're enjoying what you're doing, time flies. If you're not enjoying what you're doing, time sort of drags. But presumably time doesn't actually do that. Time doesn't actually speed up because you're having a laugh and a drink with someone you like, whereas it slows down if you find yourself leaning on a hot stove. I mean that was Einstein's example. So how long the present is at least as much a job for the psychologist and the physicist as it is for somebody like me. And I wouldn't dare lecture psychologists and physicists about how long they should take the present to be. But interestingly, the minimal unit that physics talks about, the Planck time, is so tiny that there would be a multitude of them in any indivisible perceptual unit. So we've got good reason to think that what we think of as the present is actually colossal as far as the physical measure of time is. Can I move on to question 3? I mean, if I don't manage to do justice to your questions, it's not because the questions are not interesting, I stress. It's because some of them are the big stuff. Some of them are quite easy to answer. Some of them are, how long is the present is getting to the what is time. Interesting third question, if it ever becomes possible, why isn't history littered with examples of people visiting from the future? Stephen Hawking had an argument like this. Somebody once asked me this in a lecture. I regret my answer bitterly, because the correct answer is, well, nobody said it was easy. First thing. Nobody said it was easy. I mean, think about Frank Tipler's cylinder, this gargantuan, maybe infinitely long, hugely dense thing. All David Lewis wants to say is that it could happen without paradoxes, which is not the same as saying that it's easy or that it's physically possible. I mean, it's possible that I could take some pens, throw them over my shoulder, and as they slid down to the ground, they could write out all of Hamlet on the way to the ground. Now, there's no contradiction in that, but it's hang of an unlikely. And maybe time travel is like that. Maybe it is just theoretically possible. But one day somebody asked me exactly that question in a lecture, and I didn't give them the right answer. I gave them a flippant answer, which is, we get a lot of training, we're very careful. And I thought, you're going to have occasion to regret that. And sure enough, a few weeks later, a student came to me and said, can I just ask, are you a time traveler? I was like, no, I said no, only in the sense that, I'm getting older. But one way to think about it, is, that I mentioned closed time-like curves, right? Where regions where space-time curves so that you can head into the local future and arrive back in the past. Well, a closed time-like curve generator isn't a machine in the way that a TARDIS is a machine. I mean, you get in the TARDIS, you pull a lever and you say, right, 14th century, go, and you arrive in the 14th century. Or you have something like H.G. Wells' time machine, where you've got like a set of brass dials with increasing dates. So you set the dials to 802,000 AD, and you set the machine going, and bang, it takes you to 802,000. Closed time-like curve generators aren't like that. Closed time-like curve generators are more like moving staircases. You get on, it joins two regions together, you get off. As I say to my students, there are lots and lots of moving staircases in railway stations in Edinburgh, but there's no point getting on the ground floor of an escalator at Waverley and complaining that it doesn't take you to Haymarket. It only joins together the places that it links. So a closed time-like curve generator is a bit like that. It only joins regions together. It doesn't give you free access everywhere. So if there are no natural closed time-like curve generators out there, and it kind of looks like there aren't, then it falls to us to create some, if we can. But suppose the world's first closed time-like curve generator comes online on the 1st of January 2022. Times later than that can travel back to the 1st of January 2022. But nothing can travel further back than that, right? The creation of the first closed time-like curve generator sets up a horizon at which the future can travel back to. So it may be, and this will sound strange, but hold this thought, it may be that time travel into the past is possible, but not as far back as we are, because the first closed time-like curve generator has yet to come into existence. The name for the horizon I mentioned, it's named after a 19th century French mathematician called Cauchy. It's a Cauchy horizon. Stick that in the chat box. And it may be that the first closed time-like curve generator is on the far side of a Cauchy horizon, somewhere downstream of us. So it depends how you think of time travel, right? If Doctor Who was real, if that kind of time travel was possible, we would expect to be knee-deep in people from anywhere in history. But the kind of time travel physics talks about is much more restricted. And it may be that it's, it's somewhere downstream of us. I'm sensing a couple of questions. Fourth question. Do you ever find time travel movies, books impossible to read due to your knowledge of the enormous field? It is an enormous field. My knowledge of it is not too good. It's true that I sometimes get frustrated watching time travel films. I won't name any, but put it this way, my wife, who's had to put up with a lot of this stuff, best part of 20 years, will no longer accompany me to the cinema to see a time travel film. Because there's two things. If I don't like it, I start criticizing it. That's not what a wormhole looks like. That's never a Cauchy horizon. But if I do like it, I make a little ooh noise at intervals, and she can't bear that, and I don't blame her. So I've basically fallen back on watching time travel films a solitary pursuit. But there are lots and lots of stories that I really like. There was a lovely one. It's a kind of time travel murder mystery called The Psychology of Time Travel by a novelist called Kate Mascarenhas, which I wholeheartedly recommend. It's lovely, The Psychology of Time Travel. It comes with a glossary at the back for things like closed time-like curves, and her definitions are brilliant. I don't know where she got them from. She certainly didn't get them from me. But The Psychology of Time Travel by Kate Mascarenhas is a book that I really think is top-notch. Totally consistent and very, very strange. One more question. If the speed of light was different in different universes, what would happen to light cones? Well, that's a very interesting question, because the assumption in many worlds theories is that the same basic physical laws govern all the branches. But there are versions of quantum theory where that isn't necessarily the case, where the laws of nature are sort of statistical. And all right, you wouldn't expect them to fail. You wouldn't expect the speed of light to vary, but travel far enough in your space and possible worlds. And in that case, then, I think a lot of bets about interactions with earlier stages and bumping into yourself are kind of off. I mean, people have tried to study systems where the speed of light moves at different speeds at different times, where kind of light cones you end up with light cones that are less conical and more pear-shaped, for one thing. So it may well be that different parts of the past used to be accessible and aren't accessible anymore. The short answer is it would be powerfully weird. It's not a very analytic answer, but I think it's a true one. I think there might be another question.
I have one question, another question. Okay, and that is this: that so let's say that we're presentists, that we experience the present as it is now. Yeah, and there are people. There's a saying, or there are people who say that the past is a story that we all agree on. Okay, yeah. So if we all agree on a different story, have we changed history?
Sorry, I had an unmute issue there.
Yeah.
Well, there are people who've taken something like that very, very seriously. I mean, there's a kind of, I was talking to some students about this only yesterday, and they all looked at me as if I'd gone completely mad. But the theory that I was talking about says that, look, something is only true about the past if it fits with our best evidence, right? So if that evidence changes, it's not just that our knowledge of the past has changed, it's that the past has changed. And the way that I illustrated it was this. I said, look, when I was a boy, our best evidence was that the world's largest extinct carnivorous dinosaur was Tyrannosaurus rex. And hence king, tyrant, lizard. This is the biggest. There's not going to be a bigger one, people assume. And then people unearthed a bigger one. There are bigger extinct predatory dinosaurs, one called Spinosaurus, which was a fish-eating dinosaur. It was even longer than T-Rex. So if you take the view that past facts are actually shaped by our best evidence, then the past is now different. It used to be the case that T-Rex was the biggest, and now Spinosaurus is the biggest. In other words, T-Rex was the biggest, and now it was the case that something else was actually bigger. And that used to be, long before quantum physics came along, a lot of theologians used to be exercised by these kind of worries. There was a 13th century theologian called St. Peter Damian who was much exercised by the question, could God make the past different from what it had been? And his argument was, well, God could have chosen not to make Rome or to make Rome. So God could now decide to make it such that Rome had never been founded, which is like a grandfather paradox installed by God. So I'm not sure what to make of these things, because I'm not sure how much of a concrete past we're left with if events now don't just reflect evidence about the past, but actually shape the past. But there are people who have tried to take that seriously, to make models where past facts literally change as a result of what we now do. For example, based on evidence, or in a more sort of theological context, if God willed the history had been different from what it was. I'm sensing another.
Yeah, I think there's one more question.
Yes, Delaney. I'm not.
So can we make this the last question? I think, because time's getting on. Yeah.
Zeleny, I don't think I've read that particular Zeleny. I've read Road Marks, which seems to be a many worlds kind of time travel. But I'm afraid, Malcolm, I would have to know more about the specific story that you had in mind. I'm afraid. Is that us for questions, folks? Are there any more, or are we done?
So, if that's the questions, can I hand over to David Bowler? David, you'll need to unmute yourself, and David will close the proceedings. Well, I think you will. There we go. You have to unmute, David.
Yes. I was trying to unmute, but it was blocked. I think I was trying to change the past. That was the problem. And running up against an obstacle. Well, I know that I'm almost certainly not the only person who approached this evening with Sorley MacLean's poem in mind, that Time the Deer is Running in the Wood of Hallig. And I think that time for us this evening has certainly run very fast. So we've demonstrated amongst ourselves the variable speed of subjective time. And I would like to thank Dr. Richmond for stretching our brains, possibly in some of the strange deformations that are possible in imaginary geometries. It's been very good for us. It certainly got us thinking. It will get us dreaming tonight. And so I am sure that all of us would like to join me in thanking Alistair Richmond for getting our season off to such a very good start, a very good beginning, so that we can look forward, we hope, to an exciting future over the next 6 months. And so with that in mind, thank you very much, and thanks to everybody for participating this evening.
Thank you all. Thank you all very much indeed. I've enjoyed talking to you.
Thank you.
All the best now. Bye-bye now. Take care.
Thanks.